Well, let's look at this question on Stack Exchange website. It's about divisor and the line bundle correspondence in algebraic geometry. So let's read the question. The question is like this. I know a little bit of the theory of compact Riemann surface where there is a very nice divisor line bundle correspondence. But when I take up the book of Harshon, the notion of Cartier divisor, there is very confusing. So word V divisor is the direct sum of codimension 1 irreducible components of a variety. But Cartier divisor, this description is by a set of open covering with a regular function on it, such that something. So, but there are correspondence as the author who asked this question is thinking about. For example, for smooth variety or integral, for smooth variety, for example, the Cartier divisor and V divisor, they coincide. Okay, let's say it is certainly not the direct sum of points. Perhaps it is better to understand in terms of line bundle, but Cartier divisors do not seem to be quite the same thing as a line bundle. The definition is hard to figure out. Can someone clear the misunderstanding for me and explain to me how best to understand Cartier divisor? Then here is answer: more or less line bundle equals Cartier divisor. There's one answer said more or less line bundle equals Cartier divisor. Linear combination of codimension 1 subvariety. Which is we know the definition of V divisor. For example, a point in dimension x equals 1 case for on the curve is direct sum of points. It's V divisor. And for good varieties, these two notions coincide. Good variety, for example, smooth. Then V divisor and Cartier divisor should coincide. So Cartier divisor is line bundle. Correspondence, you know, for the case of Riemann surface, they will coincide. So he responds, I figure as much, that Cartier divisor is something like line bundle, but Cartier divisor seem to be quite crude thing. It is defined in a strange way. Then some people answered, roughly speaking, you describe the points or codimension subvariety in Euro V divisors as the zero set of meromorphic functions in Cartier divisor. It is constructing the connection between Cartier divisor and V divisor. So the codimension subvariety V divisor will be the zero set of meromorphic functions in Cartier divisor. The Cartier divisor is given by an open cover UI together with meromorphic functions fi defined on each open UI in the cover, such that the change on intersection is a non-vanishing holomorphic function. such that a change on intersection is a non-vanishing holomorphic function. This precisely means that zero set is not going to change no matter which representative fi or fg you are using on the intersection. So it means on ui you have fi defined, on ug you have fg defined. The zero set is not going to change no matter which representative you're using in the intersection. You use fi to be the function of the intersection ui intersection g, or use fg. Roughly speaking, you describe the points as zero set of meromorphic function in Cartesian divisor. Yes. So as we mentioned, we describe Cartesian divisor more precisely. We will more precise describe our Cartesian divisor. Let's just finish what is the writer answered with. As for line bundle, just remember that the change on intersection is non-vanishing holomorphic function, which can also be used to glue the trivial bundle on each ui. Or more precisely, Cartesian divisor is an invertible shape of K. Maybe this description is more transparent than the original definition. It's an invertible subshape. It's an invertible shape, just an invertible shape. And he recommended people to say his proposition in Harshon. And we just we say here, what did we just say? The change on intersection ui intersection g is a non-vanishing holomorphic function. I mean the change of the on ui. I mean ui already define fi, on ug already have defined fg, but on ui intersection ug you must be defined with there is a change by phi ig on ui intersection ug. This phi ig is holomorphic. Okay. This phi ig is holomorphic. And this tells us that this will tell us is the information that the zero set defined by fi is the same as zero set defined by fg. Let's give the ordinary definition Cartesian divisor first. So let X be a variety over a field K. We call Cartesian divisor a set of pairs ui, fi, where each ui is an open set such that the union of the ui is the whole space, and where fi are elements of function field. Of rational functions on X. Such that on the intersection ui intersection with uni, the quotient quotients fi over fj and fj over fi are regular. Remark: the reader that is familiar with some more advanced techniques as Green-Hartshorne's book will recognize that the above definition actually defines the representative of a calculated answer. The reader that is not familiar with those notions can just read and take the definition as it is. For the example, it will certainly suffice to work with the above definition. For the group theoretical issue mentioned below, it is, however, desirable to have at least once indicated how to be more precise. 2. Cartier divisor. Are called the equivalent. If on all the intersections you are intersect with G, the quotients fi over gg and gg over fi are regular. One more definition. Let X be a variety over K. And let F be an element of small k as fractional field. Therefore, any two covering any open covering, ui of x the set define the Cartier divisor. I mean, surely here it means f restrict on ui. Okay. Define the Cartier divisor. Which we will call it a principal Cartier divisor. While in those above definition remarks, when we say algebra, when we say variety, we actually mean the variety is irreducible topological space, irreducible, okay? Our variety will always be reducible. Well, as we saw from the small answers of the beginning question, we say the connection between wheel divisor and Cartier divisor will be the zero set as a subvariety defined by those rational functions, the zeros of those rational functions. So you see, what we care about in the wheel divisor is as a subvariety of the whole variety X. And the information we got on Cartier divisor is first you are given an open covering ui. On each open ui you have a rational function. Well, what is important for you, you have to define using those function on each open subset ui defines subset which is 0 of this function. But the problem is, are you well defined what is your subvariety of X using this system of open covering and rational function? For example, one problem is, if you have ui and ug, on ui you have a rational function fi, and on ug you have rational function fg, how do you define the subset on ui and ug that is killed by the system fi and fg? I mean, surely on ui you can define those 0 elements, those elements in the kernel of fi, and on ug you can define the zeros, the kernel of the fg. But you can only do so, and of course you want to take the union to define it as the 0 set of ui union ug. But it only works if on the intersection of ui intersect ug, your fi and fg give you the same 0. This is why we give some more information to require that fi quotient fg and fg quotient is fi or regular. Or even stronger, and in my opinion he said the change of intersection for those rational functions on ui and uj, when you restrict to the intersection of ui intersect ug, are by non-vanishing holomorphic function. This will give you the same zeros, let you be able to glue the trivial bundles and issue I to the bundle and UI into union with UG. So we have to see more precisely how this works. Remark: the Cartier divisor can be multiplied to form an Abelian group in a natural way. For example, we take D to be system UIFI and D prime to be the system VK GK indexed by small k by k. Let's say there are two given Cartier divisor. Then we want to define operation on it. We define D plus D prime to be the Cartier divisor, that is, the open covering is given by all the intersection with I as we keep all the I and K running over the index family, index set, and the rational function is given by Fi times Gk. So this system is indexed by both I and K running over all the index set. It is easy to say that the inverse of D is given by the equivalence class So we are going to using this definition of summation. Then we can know for a given Cartier divisor D what is its inverse. Its inverse is exactly in this form. And the unique element of this Abelian group we just defined for Cartier divisor should be let's take the whole topological group as the open covering and the identity element restrict on it. So it's the identity function itself be the rational function. In particular, let's say, so the summation for D plus x1, what is it? It's take intersection of the UI with x with this UI itself. and multiplication with fi with identity with fi itself. Their index is still I, so it's the same as. So obviously this is the identity. If you want to check the inverse, is really inverse. D plus is D inverse. What is it? It's intersection is given by ui intersect with ug or ig, and the function is given by fi multiplied with fg. So what is it? In this case is 1 over fg, because our D inverse has additional function 1 over fi on ui, and so 1 over fg for eg. Well, we call them the intersection, you know. This is actually pi intersection ug times 1 over fg minus ug, but we know fi is fg on the intersection ui intersection g, so just the identity. So this is just yes, but it's not x1, but it's just ui with identity everywhere. Surely this is equivalent to x. We already defined the equivalence relation of those cutting divisors. The equivalence relation as we described. It's a definition of cutting divisor. Yes, equivalent. Two cutting divisors are called equivalent if of the intersection the quotient are regular. I want to check how different are they. Check on how different are they by their kernel. If fi gg the quotient are regular, this will tell you that fi restrict on your intersection with g have the same zero with gg restrict on your intersect with g. Because this one times gg over fi is gg, so but this is regular. Regular means this function will not have 0, or you may say gg may have 0, but also I'm telling you fi over gg is also regular, so gg cannot have 0, and same with fi cannot have 0. So their transition, they are different by a multiplication of regular function which has no 0. So they must define the same set. I mean they're 0, and let's define subvariety which must be the same. That's why we also say the equivalence class. We define the inverse, we define equivalence class. Equivalence class in this system, it doesn't have to be exactly UI or Fi. It can be any other system, but we have to be equivalent with this relation, which means they're different. Yes, we know what I mean. This by definition, just as we described. Okay. Oh, I mean, this Abelian group is all the Cartier divisor. Quotient with equivalence relation. And those is the summation of the equivalence class. Okay. This is the final equivalence class. For example, if I write more precisely, so I choose another d prime inverse, which is just UG. Let's say 1 over, no, I don't write 1 over, okay, I just say GG, which is equivalent to UI 1 over Fi, which is equivalent to 0 first. On each any UG intersect with Y is V. Here I use V. For any UG intersect with UI, the difference between those two original functions which is first GG quotient 1 over Fi, which is the same as GG times Fi, and on the other hand 1 over Fi quotient by GG, all regular. Then we have to see this. The summation defined on the equivalence class give you a well-defined summation, and this indeed inverse. I mean, you have to set this is well-defined in the sense that what you have really defined representative class of D class with representative class of D prime. Is the representative class in this. This is defined in this way. What you have to check is if I choose another representative of this class, with another representative class, this class, I do definition using D prime. And I have to change both to change one. Equal to the question mark is actually here. So now we start with this different representative and we do summation. You see, we don't have to be so confusing. What we have to do is we don't have to just check it for the university, we check it in general. This is just a particular case of the general case. I need to check whether when I change a representative of the what I am checking is actually this. I don't have to check this. Once I can check this is well defined, I don't have to check this. So all I have to check is this is well defined. 79, I'm going to check this. So suppose D is equivalent to D prime. Let's check D plus D prime. If this is okay, then it's well defined. Okay, so what do we have to check? Really, we have to check. So first, suppose this is UI, this is UG, sorry, this is WG. To keep the same notation, UG Twitter, FG Twitter, D prime, suppose it's W K GK. Then, by the definition, summation D plus prime elements are given by intersection multiplication each position. On the other hand, D prime D3 plus D prime is given by the same way that yes. Like this, yes, exactly. Exactly nice. And then we have to check the equivalent. Yes, we have to check the equivalent, so we have to check take any index. So UI intercept UK1 intercept UG intercept UK2. On this circumstance, we have to compare Fi times GQ1 FG Twitter times GQ2. We have to compare this to rational function of this intersection. So this is arbitrary open in this cleans offset is arbitrary open in this open covering. This is then defined for a homomorphic function of this. This is homomorphic function of this. We have to see their transition change morphism holomorphic, say regular. This is homomorphic. This is the complex case. And then let's see. So first let me see. Check this one. And then we have to check this one. Are they both regular? each UI intersect with EG. Fi over FG theta, and FG theta over Fi are all regular. So UI UG theta. But here is more VT1 VT2. So UI intersect with EG. These are all regular. Surely, in particular, on this even more smaller restriction. It's still regular. And then how about GQ1 over GQ2 and GQ2 over GQ1? Are they regular? Yes, they are, because they are the same. I mean, GKI restrict on K. GKI intersect with KG, the same as GKD restricting GKI over KG. Sure, they are regular. So yes, we are defined. Okay, I agree. So by this operation of summation we define on this set, we check that it become abelian group. So that we divide the from abelian group. Let's not define what is called a Picard group. Let X be a variety working. And the quotient group. Formed by dividing the group of Cartesian divisors. By the subgroup defined by the principal Cartesian. Which will remark this is normal subgroup actually. E is called the Picard group. And denoted. So Picard group, basic Picard group. box. Okay, smooth right. Okay. And then we can define the divisor. Is finite. Abstract sum. Will be reducible smooth dimensional. Some writing. And the principle. Is the formula. Over the zeros and pull. Commune is multiplicity of a rational function, as we can expect. And we denote just by F plus bracket, the group of radii. Is denoted so, as you can expect it, since the elements are formal sum, abstract sum, could dimension as a right is identify a summation just by abstract sum, formal sum together will do sum. And you can expect with the zero element. Have a quotient. Of it divided out by the subgroup. Of the principal divisor. Is called class group. And denoted by CL. X is smooth. We can associate to each category. The video. That is defined on UI. Is given by the zeros and poles in the file. And then taking the union of all of these. We obtain a set of closed dimensionalized right. While the smooth condition here will be used to show that the set of codimension, the union of all those separated given by zeros and poles, and we close them together, give the codimension and separate. Okay. We gave this we'll explain this when we have time, so we give this just index. Smooth 0, 0, 1. Okay. And we stop this time here.